Right. Thanks. Yeah, so thanks very much for the invitation to visit and speak here. It's very nice to be at IAS. So yeah, so today I'm going to talk about meandric systems, which I'll define in just a moment. And this will be based on joint work with Jacopo, Borga, and Minjae. Okay, so let me start off by defining a slightly different object, which is not the main one that I'm going to talk about, but which is maybe closely related. So a meander is a configuration consisting of a simple loop in the plane, which does not cross the real line without, which does not touch the real line without crossing it, and which crosses the real line exactly at the points 1 through 2n. Okay, and we view the configuration as being defined modulo homeomorphisms from R2 to R2, which fix the real line. So here's an example of a meander. I think this one has size 12 or size 6 because there's 12 total intersection points. Okay, so the study of meanders dates back to work by Henri Poincaré in about 1912. And these things arise in kind of a huge number of different areas of math and physics, including polymer folding, combinatorics, topology, probability, partial differential equations, moduli spaces, all kinds of different and perhaps sometimes surprising things. And if you want to read more about all of the different places where meanders show up, there's kind of a nice short survey article by Zvankin, which discusses this. Okay, so despite their connections to lots of different other mathematical objects, meanders are kind of notoriously difficult to study, even to simulate. So there's very few rigorous results concerning meanders, and kind of the best known algorithm for exactly sampling a meander takes an exponentially long time in the number of vertices. So it's hard to even do kind of numerical simulations of these things to guess what the answers should be. Nevertheless, there is a conjecture for the enumeration of meanders, which comes from the physics literature, work by Di Francesco, Golinelli, and Guiterre. And they conjecture that the number of meanders of size n should grow like a to the n times n to the alpha, where a is about 12 and alpha is this kind of crazy looking explicit number here. So I'll say a little bit more about this conjecture momentarily, but it's kind of proving this conjecture is still wide open. There's not very much known rigorously about this enumeration problem. Yes?
Any formal statement about the fact that they are hard to simulate?
I think there can be a formal statement, like, or you mean like a rigorous statement to the effect that there does not exist a polynomial time algorithm to simulate them. I'm not aware of such a statement. Maybe it's possible that there is one and just nobody has found it yet. Okay, so that's a meander. So kind of very interesting, very simple to define, very hard to do much of anything with them. So in this talk, I want to discuss an object which a priori looks like it might be maybe more complicated than meanders, but which actually turns out to be easier to study, namely a meandric system. So meandric systems are basically defined in the same way as meanders, except you don't have this constraint that there's only a single loop. So a meandric system is a collection of disjoint simple loops, which do not touch the real line without crossing it, and which intersect the real line exactly at these points 1 through 2n. Okay, and again, it's viewed modulo homeomorphisms from R2 to R2, which fix the real line. Okay, so a meandric system can be thought of as kind of like a coupled collection of meanders, because each of these individual loops, if you kind of forget all of the other loops, each individual loop can be viewed as a meander, and the meanders are kind of coupled together so they don't intersect or cross each other. Okay, so a meander can be thought of as just a meandric system subject to the constraint that there's only one loop. Okay, so there's been a bunch of recent works in probability and combinatorics that looked at these meandric systems by various authors, some of whom I've listed here. And I'll give a kind of an overview of what's known in just a second. And meandric systems are also kind of interest in statistical physics, because a meandric system is kind of equivalent to a certain variant of the ON loop model on a planar map. So there's kind of various different perspectives that you can take on these meandric systems. All right, so it turns out that meandric systems are a lot easier to analyze and to simulate than meanders. And the reason is that meandric systems are in bijection with various simpler combinatorial logics. So one way of phrasing this bijection is in terms of arc diagrams, aka non-crossing perfect matching. So an arc diagram consists of a collection of disjoint arcs in the upper half plane, each of which joins two integers between 1 and 2n. So here I've shown kind of two examples of arc diagrams. So there's one arc diagram in red here, and then another arc diagram in blue here. Okay. And it's not too hard to see that meandric systems are in bijection with pairs of arc diagrams of size n. So if you're given a meandric system, you can always generate two arc diagrams by just kind of looking at the excursions of the meandric system loops above the real line and the excursions of the meandric system loops below the real line. Conversely, if you're given two arc diagrams, you can draw one above the real line and one below the real line, and that generates a collection of loops, which is a meandric system. Okay, so we have kind of this easy bijection between meandric systems and pairs of arc diagrams. And arc diagrams, in turn, are in bijection with 2n step excursions of simple random walk on the integers, i.e. Dig paths. Okay, and the way that you can get the walk path corresponding to an arc diagram is we just follow the real line from left to right. Every time we see an arc which goes from left to right, our walk takes an upward step. And every time we see an arc which is kind of joined to something to the left, the walk takes a downward step. So if we wanted to generate the walk corresponding to this red arc diagram, we would go up, down, up, down, up, down, up, 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 down, down, down. Okay, and so that gives us this walk path here. All right, so if we wanted to, so there's a number of kind of immediate consequences of this bijection. First of all, the number of meandric systems of size n grows like the square of the nth Catalan number, because the Catalan number counts the number of these walk excursions, and meandric systems are in bijection with pairs of walk excursions. Okay, so already we have an enumeration formula for meanders, which is already like a lot better than what's known for meandric systems. Furthermore, if we wanted to sample uniformly from the set of all meandric systems of size n, then we could do that by just sampling two independent uniform random walk excursions, and then generating the two arc diagrams for these independent uniform random walk excursions, and then kind of forming the meandric system from the pair of arc diagrams. Okay, so we can kind of reduce the study of meandric systems, at least to some extent, to the study of kind of much simpler objects. All right, so in this talk, I'm going to be interested in the geometric properties of uniformly sampled meandric systems. Okay, so at first glance, one might think that it shouldn't be too hard to prove things about the geometry of these uniform meandric systems, because they're in bijection with pairs of simple random walks, and simple random walks are really easy objects to analyze. So we should think maybe we can just reduce everything to questions about simple random walk, and thereby have a very good understanding of how these uniform meandric systems behave. But the problem here is that the set of loops in the meandric system is an extremely complicated functional of the pair of walks. So it's very difficult to actually read off kind of nice descriptions of the of features of the meandric system in terms of this pair of walk excursions which are encoded. Okay. Nevertheless, there has been some progress in improving geometric properties of these meandric systems. And let me now mention some of like the most natural questions that one might want to ask about meandric systems, and then say kind of what's known so far. Okay, so one very natural question that one might think of about these uniformly sampled meandric systems is how many loops do they typically have? Okay, so remember that we're not specifying how many loops a meandric system has. The total number of loops is a random variable. And it was shown in work by Ferret and Thevenin very recently that the number of loops in a uniformly sampled meandric system typically grows like kappa times n, where kappa is a deterministic constant, which can be expressed as an explicit sum over meanders. So there's not a closed form expression for kappa, but one can get kind of arbitrarily good numerical approximations of this number, kind of at least in principle. And so we have a pretty good understanding of how many loops a uniformly sampled meandric system has. Another question we might want to ask is kind of how big is the largest loop of the meandric system? So one way of thinking about the size of the loop is maybe we could look at like how many intersection points with the real line does this largest loop have? Okay. In this case, things are much less well understood than for this question of the number of loops. So it was shown by Kargan that the largest loop of the uniform meandric system has at least C times log n vertices with high probability, where C is some explicit constant. Prior to our work, this was kind of actually the best known lower bound for the size of the largest loop. Nevertheless, Kargan did some numerical simulations, which suggested that the largest loop should have size of order n to the alpha, for alpha maybe about equal to 4/5. And so of course his largest bound was very far off from the value that was kind of predicted by the simulations. All right, maybe kind of a next level question that one can ask after wondering about the size of the largest loop. We could ask, is there typically just like one big loop which dominates in our uniform meandric system, or are there kind of lots of big loops of comparable sizes? Equivalently, like is the second largest loop or the third largest loop kind of approximately the same size as the largest loop, or are the sizes decaying pretty rapidly after you see the biggest loop? Okay, so this question, the answer is also not known rigorously. But there has been some related work by Kurian, Kozma, Sidaravaikas, and Trunier in the context of the so-called infinite noodle. So this question of whether there's a single dominant loop is closely related to the existence of this so-called infinite noodle, as I'll explain a bit later in the talk. Okay. And then finally, another natural question to ask about the geometry of these meandric systems is whether they have some kind of scaling limit with respect to some reasonable topology as the total number of as the size of the meandric system goes to infinity. Yes.
What about the diameter of the largest loop? Is it supposed to be similar to the size or not?
I will get to that in just a moment. But you can also ask. Well, I guess there are different notions of diameter you could ask about. But we kind of have predictions for the asymptotic growth rates for all of them.
In the typical loop, the loop containing 0, that's kind of the same as all these questions.
No, so the largest loop is not necessarily going to be the one containing 0. In fact, if the largest loop has size of order n to the alpha, where alpha is less than 1, then typically the origin is not going to be on the largest loop because the origin is kind of uniformly distributed over the vertices.
Maybe it has the right tail. Right tail.
Yeah. So you could ask about the tail of the size of the origin containing loop. That's another kind of related question to the size of the largest loop. Okay, so what I want to present in this talk is first of all conjectures for the answers to each of these questions: the size of the largest loop, whether there's a single dominant loop, and also the scaling limit as n goes to infinity. And also I'll present some rigorous results which are kind of consistent with these conjectures, and give at least partial answers to some of these questions about the large-scale geometry of the uniform meandric system. Okay. So before I proceed with the conjectures, does anybody have any questions about just this basic setup?
Yeah, I was just wondering, have people studied non-uniform weights on these? So let's say you wait longer, you put in other weights that might get closer to the uniform meander.
Right, so I don't think there's been any rigorous study of non-uniform weights. And if you put weights on this thing that get you kind of close to the uniform meander, it seems that we don't really have a whole lot of tools for analyzing this thing, kind of similarly to the case of the meander itself. But we do have conjectures for what should happen if you weight by like the total number of loops.
Yeah, that's what I was thinking.
So, if you kind of bias so that there tends to be few loops, we can also conjecture about we also have some conjectures about the scaling limit of that, which we can maybe talk about after. Okay, so let me now discuss what we conjecture about these meandric systems, and I'm going to begin by stating a scaling limit conjecture, because kind of the conjectured scaling limit is going to be the basis for our conjectures about various exponents associated with the meandric system. So in order to talk about scaling limits of meandric systems, we need to specify some sort of topology of convergence that we might want to look at for these combinatorial objects. And one convenient way to do that is to view a meandric system as being a planar map, i.e. a graph embedded in the plane, viewed modulo orientation preserving homeomorphisms from the plane to itself. Okay, so to do that, we can think of the vertices of the meandric system as being like the intersection points of the meandric system, or of the loops with the line. And then we can think of the edges as being the segments of the loops and the segments of the line that go between the intersection points. Okay, so these pictures that I was showing previously of a meandric system can also be thought of as representations of the meandric system as a planar map. Okay, because this is already just a planar embedding of the meandric system. Okay, and this planar map has a bit of additional structure besides just being a planar map. Namely, it's decorated by a Hamiltonian path, a path that hits each vertex exactly once, and that path is just obtained by traversing the real line from left to right. Okay. This planar map is also decorated by a collection of loops, i.e. simple cycles in the graph, which are the loops of the meandric system. Okay, so a meandric system is kind of equivalent to a planar map decorated by a Hamiltonian path and a collection of loops. Okay. Now, there's a pretty substantial literature concerning the scaling limits of various types of random planar maps. And in particular, there are a number of different possible topologies that one can put on planar maps, i.e. Different possible ways of talking about scaling limits for planar maps. For example, one option is to look at, is to kind of view this planar map as a metric space equipped with the graph distance. And then ask whether it converges with respect to some version of the Gromov-Hausdorff topology for metric spaces, which are also decorated by kind of a distinguished collection of curves. Okay, and it's kind of easy to generalize Gromov-Hausdorff convergence to the case of curve-decorated metric spaces, as that gives us kind of one possible choice of topology here. Another possible topology is to take this planar map and kind of embed it into the plane in some canonical way, for example, via a circle packing or a harmonic embedding, or via the Riemann uniformization theorem or what have you. And then you can view this thing as like a Hamiltonian path and a collection of loops that are actually drawn in the plane in some explicit way. And then you can ask whether this path and this collection of loops has some sort of scaling limit. Okay, so there are a couple of topologies that one can consider. But for the purposes of this talk, I want to be maybe a little bit vague about the particular topology, to really expect convergence with respect to any reasonable topology that one might want to put on these things. Okay, so with that said, we can then ask kind of like what should the limiting object of this uniform meandric system be? Okay, well, the meandric system is represented by a planar map, which is decorated by a path which hits every vertex, and also a collection of loops. So limiting object should be represented by some kind of random metric space, or some kind of random surface maybe, which will describe the limit of the geometry of the underlying planar map. And then this random metric space should be decorated by a space-filling path which hits every point of the metric space, because this Hamiltonian path here hits every vertex of the meandric system. And this space should also be decorated by some collection of loops, which represents the scaling limit of the meandric system loops. Okay, and we have a precise conjecture for what this limiting object should be. Namely, we conjecture that the scaling limit of this uniform meandric system, viewed as a planar map, should be given by Liouville quantum gravity with parameter gamma equal to the square root of 2, decorated by an SLE8 curve, which is going to describe the limit of this Hamiltonian path, and a conformal loop ensemble with parameter kappa equal to 6, which should describe the scaling limit of the meandric system loops. Okay, so I think many of you in the audience are very familiar with these objects. For those of you who aren't, I want to say just briefly what each of these objects that appear in our scaling limit result or our scaling limit conjecture are. So first of all, we have this Liouville quantum gravity sphere. So a Liouville quantum gravity sphere is a certain type of random surface, but it's not really a surface in the literal sense. Instead, it can be represented in terms of a random metric, i.e. a distance function, and a random measure, which live on the two-dimensional sphere. Okay, so it's kind of too rough to actually have a notion of like derivatives and tangent vectors and so forth, but you can still define like the Riemannian distance and the Riemannian volume form associated with this, this kind of random rough surface. All right, an SLE8 is a random space-filling curve. And the particular version of SLE8 that we want to look at is going from infinity to infinity in the Riemann sphere. All right, so it's a curve that starts and ends at the same point and fills in all of space. And then CLE6 is a countable collection of random fractal loops, which each locally look like Schramm-Loewner evolution curves with parameter kappa equal to 6. So in particular, these loops are allowed to kind of hit each other to kind of have self-intersections, but they're not allowed to have self-crossings. So they're kind of a fractal type of loops. And I'll show a picture in just a minute. And one point that I want to emphasize in this scaling limit result is that at the discrete level, if we see the planar map, we see Mn, and we see the Hamiltonian path Pn, then we can determine what is gamma n. So we can determine the collection of loops because the edges hit by the path are precisely the complement of the edges hit by the loop. Okay, so kind of the path and the loops determine each other at the discrete level. But the conjecture is that they should be independent in the scaling limit. We think that in the scaling limit, this SLE8 and this CLE6 should be independent from each other. Kind of intuitively, the reason why we might expect this, or at least the reason why this could plausibly be true, is sort of the dependence between the path and the loops at the discrete level is depending only on kind of microscopic information about the meandric system. And when we pass the scaling limit, we really only see the macroscopic information. So the dependence between these objects kind of disappears in the scaling limit. Okay.
So does this, once you specify these, is that a unique specification, or I mean, does that, or do you have to say more about? Are there several systems which have this property, or is it just a unique one?
What do you mean? A unique system with what property?
Well, what the ones you've written down.
Oh, yeah. So these are all kind of explicitly defined things. So it's not like these properties are uniquely characterizing this thing. They can all be defined explicitly, but I was just giving kind of a basic description of what they are, because for the sake of time, I don't want to get into the technical details of how to actually define these things.
But you have a well-defined definition.
Yeah. So there's
which is unambiguous. Right?
Yeah. So there's an unambiguous definition of these things in continuum, and there's lots of things that can be proven about them. So they're kind of very well understood objects mathematically. All right. So here I've shown a picture of a sample of a large uniform meandric system, which was simulated by Minjae Park. And here in the picture, so the left picture is showing like the arc diagram representation. And then the right picture is showing the embedding of the meandric system into the plane via the harmonic embedding. So this embedding is kind of specified by the condition the position of each vertex is equal to the average of the position of its neighbors. Right, and then the large loops of the meandric system are each colored in a different color. So like this red is the largest loop, the orange is the second largest loop, and then like the green and the purple and the blue are other large loops of the meandric system. Hi. So it's a couple of features that I want to emphasize here. One is that kind of in this harmonic embedding picture, we expect that the collection of loops should be converging to this conformal loop ensemble with parameter kappa equal to 6. And so these colored loops over in this picture here can be thought of as a discrete approximation of conformal loop ensemble loops, at least conjecturally. Okay, so as you can see, they're very rough fractal sort of loops. And then in this picture on the left, you can see that it's kind of very chaotic. Like the loops are going all over the place in this meandric system, and they're kind of tangled up amongst each other and so forth. And this is kind of consistent with the fact that the loops are a rather complicated functional of the arc diagrams that encode the meandric system.
Can I ask a question?
Yeah.
So is this a quantum sphere or quantum disk?
Yes, this is the disk version. So it's slightly. So you specify a collection of boundary vertices, which have to be kind of not matched to anything with respect to one of the arc diagrams. So it's a slightly different thing than the meandric systems that I was showing previously, because I wanted to have a distinguished boundary in order to define the harmonic embedding of the planar map. Okay, so hopefully this gives you maybe a little bit of a sense as to what these things actually look like. Yeah.
So we can explain the harmonic map is defined as each coordinate is average of.
Yeah, so the two coordinates are discrete harmonic functions on the planar map. So the position of each vertex in the plane is equal to the average of the positions of its neighbors.
Of its neighbors in which sense?
Of its graph neighbors, like the other vertices that are connected to it by an edge.
By an edge, you mean by meander and by the line?
Yeah. Yes. Yeah. So the edges are the segments of the loops and the segments of the line. Okay. All right. So building on this this scaling limit conjecture, we can also conjecture some values for, before I do that, I want to say maybe a little bit about our justification for this conjecture. I'm not going to get into very much detail, but I maybe want to give a little bit of a sense as to like why we might expect this conjecture to be true. First of all, our meandric system can be encoded by a pair of independent random walks on the integers. Because remember, these arc diagrams are in bijection with excursions of simple random walk. There's kind of a general theory, kind of a very deep theory, which some of you are familiar with, which suggests that whenever you have planar maps that can be encoded by independent random walks, you should kind of be getting square root of 2 Liouville quantum gravity and an SLE8 in the scaling limit. So if you don't know anything about mating of trees, maybe just ignore this part, and you can just think of this as saying that it's kind of maybe already prior to our work, it was kind of already known to experts that you should be seeing the square root of 2 Liouville quantum gravity and this SLE8. So part that was kind of new in our work is the conjecture that the collection of loops should be converging to this conformal loop ensemble with parameter kappa equal to 6. And this conjecture comes by way of kind of a combination of physics heuristics and numerical evidence. So the physics heuristics are based on some work by Di Francesco, Golinelli, and Guiter in 1999. This is the same paper in which they conjectured the asymptotic formula for the enumeration of meanders. Kind of the arguments of Di Francesco, Golinelli, and Guiter can kind of be rephrased in terms of SLE and LQG language as saying that the scaling limit of the uniform meandric system should be given by Liouville quantum gravity with with gamma equal to this funny looking parameter here, decorated by 2 independent SLE8s. So for the meander, we have like a similar scaling limit conjecture, except instead of an SLE8 and a CLE6, you get 2 independent SLE8s, and the Liouville quantum gravity parameter is different. So you have kind of a different underlying random fractal surface. So this was observed and worked by myself and Borga, and myself, Jacopo, Borga, and Shin Sun. It turns out that if you kind of take this heuristic argument from the papers of Di Francesco, Golinelli, and Guiter, and Borga, myself, and Sun, and you apply it to meandric systems instead of meanders, then you can kind of get kind of a heuristic justification for the scaling limit conjecture for these meandric systems, which I just stated. So it's kind of a generalization of the arguments used to get conjectures for scaling limits and exponents for meanders. And then we also have a substantial amount of numerical evidence supporting our conjecture, some of which comes from an earlier paper of Kargan, and then we, by which I mean mostly Minjae, also did some simulations of these meandric systems, which are also consistent with our conjectures. Okay, so in order to explain kind of how these numerical simulations can give evidence for our conjectures, I first want to state a conjecture for a certain exponent associated with the uniform meandric system, namely the exponent for the size of the largest loop. If sigma n is a uniform meandric system of size n, then what we conjecture is that for each, so suppose we have this uniform meandric system of size n, and for each k, we look at the kth largest loop in the meandric system. So on with the kth most intersection points with the real line. And what we conjecture is that if we fix k and we send n to infinity, then asymptotically the number of intersection points with the real line of this kth largest loop should grow like n to the alpha plus a little O of 1 error in the exponent, where alpha is this number here, which is about 0.79. Okay, so this conjecture kind of comes from the scaling limit conjecture by computing the square root of 2 Liouville quantum gravity dimension of a CLE6 loop by means of the KPZ formula. So for those of you who don't know about SLE LQG things, you can think of this as just being you kind of match an exponent in the discrete setting to a known exponent in the continuum setting. Okay, so it's kind of like can be viewed as maybe like a consequence or like a corollary of the conjecture for the scaling limit. And this conjecture is one that can be very easily checked numerically, because you can simulate large meandric systems, look at the size of the largest loop, and then just look at how rapidly does it grow. It's kind of already consistent with the simulations of Cardan that I mentioned earlier, because our projection exponent for the largest loop size is pretty close to 4/5, and Cardan's simulations were showing that the largest loop should grow like n to the 4/5. And then Minjae did also some simulations for the k largest loops of the meandric system for k equal to 5, and then produced this very nice picture here, which is showing kind of a scatter plot of the log of the largest loop size versus the log of the number of total number of vertices of meandric system. And as you can see, if we do this log plot for each of the 5 largest loops, the number of vertices in the loop is growing like the size of the meandric system to the power alpha, where alpha is numerically very close to the predicted value. So these slopes that you see here are kind of the numerical estimates for the value of the exponent for the largest loop, and as we can see, they're very close to the actual conjectured value.
Does the work of Di Francesco et al. Make any predictions about this system, or?
So they just considered meanders, not meandric systems, but it turns out their arguments can kind of be adapted to treat meandric systems.
And would they give this? I mean, is that consistent with your picture too, or?
Yeah. So the kind of one of the sources of our conjecture is just adapting the Di Francesco Golinelli detail argument to meandric systems. So everything that they do is totally consistent with our conjectures. Okay. So that maybe concludes the conjectural part of the talk. So we have the scaling limit conjecture, and we have conjectures for various exponents, such as the largest loop size. And we have pretty strong heuristic and numerical evidence. So these are conjectures that we have maybe a very high degree of faith in. And I now want to discuss a bit about what we actually prove rigorously about these meandric systems. Okay, so the first result that I want to present can be thought of as a statement to the effect that the uniform meandric system admits macroscopic loops. Okay, so in order to state this precisely, I need to formulate exactly what we mean by macroscopic. And for that purpose, it's convenient to have in mind a particular number associated with meandric systems, or equivalently with square root of 2 Liouville quantum gravity, which is the Hausdorff dimension of the square root of 2 Liouville quantum gravity metric space, and which we're going to denote by D. So this number is not known explicitly, but we do have fairly good rigorous upper and lower bounds for this number. Namely, we know that it's between 3.55 and 3.63. Okay, and a bunch of our results about this meandric systems are going to be stated in terms of this number D. Okay, So the first place where this number d appears in the setting of uniform meandric systems is that d is the exponent for the graph distance diameter of the uniform meandric system viewed as a planar map. Okay, so remember that before we were taking this uniform meandric system and we're identifying it with a planar map whose vertices are the intersection points of the loops with the line and whose edges are the segments of loops and lines between the intersection points. We can show that if we view this planar map as a graph and we just look at the maximum graph distance between any two vertices, then that's going to grow like n to the 1 over d as n goes to infinity. Okay, so this statement comes from some fairly non-trivial results in SLE LQG random planar maps theory. In particular, it comes by way of a comparison to the so-called mated CRT map, which can in turn be can be estimated using LQG techniques by means of the mating of trees theorem. So these are kind of quite difficult results in LQG theory, but there's kind of established techniques maybe for how you estimate diameters of random planar maps using SLE and LQG.
So just to make sure that I understand, so this means that if you take points from 1 up to n and put a meandric system on them, then to get from one point to another, either by going on the real line or by taking a loop edge, you need at most n to the 1 over d steps.
Yes, that's correct. Okay, so right, so we have this. We know the kind of the asymptotic growth rate of the graph distance diameter. And what we show is that if you take this uniform meandric system, as you look at the largest meandric system loop, view it as a subset of this planar map, then the graph distance diameter of this largest meandric system loop with respect to the graph distance on Mn is also growing like n to the 1 over d as n goes to infinity. So the graph distance diameter of the largest meandric system loop is of the same order of magnitude as the graph distance diameter of the whole meandric system. Meaning that the largest loop is kind of macroscopic in the sense of graph distances. Okay, so the proof of this statement kind of is by means of a combination of two different steps. So the first step is kind of a purely discrete argument based on a parity trick, which allows us to show that the uniform meandric system is going to admit loops which are macroscopic in a certain precise sense, but not exactly in terms of graph distance diameter. And then we use continuum arguments. So again, using this mating of trees stuff and also estimates for the Liouville quantum gravity metric, which allow us to say that a loop which is kind of macroscopic in the sense of this first step is in fact going to have a graph distance diameter bounded below by something of order n to the 1 over d. Right, so there's kind of a short and somewhat tricky but elementary discrete argument, followed by an argument which is also short but which is very non-elementary using continuum theory. And maybe if I have time at the end of the talk, I can say a little bit about actually how these. I can actually give some of the details of this discrete part of the argument. For now, I want to just first maybe give a little bit more context for this result. So first of all, we can kind of think of our result as being maybe a random planar map analog of some recent results for the ON loop model on a lattice by some of these authors here. So Ron, who's in the audience, and some of his various collaborators. And what they showed is that if you take the ON loop model on the hexagonal lattice, then for certain parameter values, it's going to admit macroscopic loops. So we prove kind of an analog of this for a version of the ON loop model on random planar maps, namely this meandric system. We also show that it admits macroscopic loops. And then I also want to mention a consequence of our main result, which is that so we know that the largest loop over meandric system has graph distance diameter at least n to the 1 over d, which in particular implies that it has to hit at least n to the 1 over d vertices, because it's a connected subset of the graph. Okay, so we get the number of vertices of the largest loop of the meandric system is at least n to the 1 over d, which by our known bounds for d is at least n to the 0.275. Okay, so this is kind of a lot worse. Still kind of far from this conjectural value for the largest loop size, which was this 0.793. But nevertheless, it's a lot better than the previous rigorous lower bound for the size of the largest loop, which was just logarithmic in n. Okay, and we expected it would require kind of substantial new ideas to improve this bound for the number of vertices of the largest loop, because one would have to somehow show that the meandric system loop is a lot rougher than a graph distance geodesic. So it has to have a lot more vertices in it than a graph distance geodesic would. And it's not entirely clear, how one would do that using the techniques that we currently have available. So for the time being, this is maybe the strongest result that we can get in terms of lower bounding the sizes of the loops in the meandric system. Okay. So in order to introduce maybe some of the other results that we prove, I need to introduce kind of the infinite volume version of meandric systems, which is what's called the uniform infinite meandric system. Okay, so what this thing is it's an infinite meandric system, which can be obtained from the uniform meandric system of size n by kind of sampling a uniform vertex, i.e. a uniform intersection point of the loops with the line, and then taking a local limit at that intersection point in the sense of Benjaminian Schramm. And this local limit was shown to exist in the work of Foray and Thevenin. Okay. Another way of defining a uniform infinite meandric system is to think back to the kind of the bijection between meandric systems and pairs of excursions of random walks. And instead of taking two independent uniformly sampled random walk excursions, you take two independent by infinite random walks on the integers. And then you do exactly the same construction, and you produce this infinite meandric system. That's this uniform infinite meandric system. Just like in the finite case, the uniform infinite meandric system can be viewed as an infinite random planar map, which is decorated by a bi-infinite Hamiltonian path, which is obtained just by following the real line from left to right. And also it's decorated by a collection of loops, except that some of the loops can conceivably not actually loops, but rather bi-infinite paths. Because it's possible that when you do these two infinite arc diagrams, that some of the loops that they form don't actually close up. So you could actually have some bi-infinite paths that are kind of alternating between tracing the arcs on top and the arcs on the bottom, and which kind of go on forever and never actually close up into a loop. Okay, so this is one of the maybe one of the crucial differences in the infinite volume case as compared to the finite volume case. And I'll discuss these potential bi-infinite paths some more momentarily. Okay, so right. So the bi-infinite paths in the uniform infinite meandric system were studied in a previous work by Kurian, Kozma, Staravicus, and Tournier. And what they showed is that there is most one infinite path in the uniform infinite meandric system. Okay, so you look at all of these loops and bi-infinite paths formed by these two independent infinite uniform arc diagrams, and they showed that there can be at most one of these bi-infinite paths. Okay, and they conjectured that in fact there are no infinite paths. Okay. So in their terminology, an infinite path in this uniform infinite meandric system is called an infinite noodle. They prove that the infinite noodle, if it exists, is unique, and then they conjecture that it does not exist. Okay, and this conjecture is kind of also consistent with our conjectures for the scaling limit of the uniform infinite meandric system, or with our conjectures for the scaling limits of meandric systems, because kind of the natural extension of our conjecture to the infinite volume case is that you should be getting a Liouville quantum gravity surface with a whole plane topology, again decorated by an SLE8 and a CLE6. And the CLE6 is just a collection of closed loops. Like the CLE6 and the whole plane does not have any bi-infinite paths. And so, it's natural to think that maybe this discrete model also does not have any bi-infinite paths. Okay. So we spent a bunch of time trying to prove this conjecture. in the setting of the uniform infinite meandric system. And we weren't successful in proving this, but we were able to prove a variant of this for what's called the uniform infinite half-plane meandric system. Okay, so the uniform infinite half-plane meandric system can be defined in a number of equivalent ways. One way to define it is we start with this uniform infinite meandric system from the previous two slides. We look at the infinite downward pointing ray started from the point 1/2, 0. And we cut all of the loops. We imagine we kind of take a scissors and cut along this infinite ray. So all of the blue arcs which cross this ray get cut into two pieces. And then after we've cut them, we kind of just match them back up in kind of numerical order. So we look at all of these ends of arcs that we have left. If we cut along this green infinite ray, and we match like the first two to the left, and then arcs 3 and 4 to the left, 5 and 6 to the left, and so forth. And we do the same with these ends of arcs to the right. Okay, and this is going to produce for us a new infinite meandric system, which has a different law from the original one. And we call this the uniform infinite half-plane meandric system. Another equivalent way of defining this thing is you can do kind of the same construction as in the setting of the uniform infinite meandric system, except that one of your random walks, instead of being an ordinary two-sided random walk, is a two-sided reflected random walk. And if you do that, and it's not too hard to check, that's going to give you exactly the same thing as this cutting and rematching procedure. Okay. And so we have this uniform half-plane meandric system. And the reason why we think of it as being half-plane-like is that it has a distinguished boundary, namely these pairs of matched arcs that we got when we kind of cut and re-glued can be thought of as like the arcs corresponding to the boundary of this infinite meandric system. Okay, and so it has it has an infinite number of vertices, and it also has an infinite number of boundary vertices, and so it's kind of a half-plane-like object. Okay, and just like in the case of other versions of the meandric system, we can view it as a planar map decorated by a collection of loops and possibly by infinite paths. And for LQG people, this can be thought of as like the meandric system analog of the square root of 2 Liouville quantum gravity wedge. All right. So what we show is that almost surely there are no infinite paths in the uniform infinite half-plane meandric system. So we weren't able to do it for the whole plane version, but for the half-plane version, we can rule out these infinite paths. And furthermore, there are in fact infinitely many loops in this half-plane meandric system, which disconnect the origin from infinity in the upper half-plane. Okay, so here I've shown a couple of these disconnecting loops, one in orange and one in purple. So we have kind of an infinite sequence of loops which are disconnecting 0 from infinity in this uniform infinite half-plane meandric system. Okay, and this proof does not use any continuum theory. It's by means of like a purely discrete Burton-Keynes style argument, where we kind of we show that there's not enough places for infinite paths to go. So it's kind of just a fairly short elementary argument, which does not need any of the continuum theory. And it's weaker than the non-existence of an infinite path in the uniform infinite meandric system, but it still seems like maybe some nice progress in the right direction. Okay, so how much time do I have left? 5 minutes. Okay. Okay, so in that case, maybe I will skip this discussion. So basically, the idea is that you can construct a path in the uniform infinite meandric system, which should be converging to an SLE6 curve from 0 to infinity. And you can simulate it, and it does indeed look like an SLE6 curve. But instead of discussing the details of that, let me talk about kind of maybe an analogy between problems with meandric systems and questions about percolation type models on a fixed lattice. So let's look at our uniform meandric system, and let's look at all of the half integers, which are kind of between the intersection points of the loops with the line. Okay, and we color these half integers in an alternating fashion. So green, orange, and so forth. Okay, and then what we're going to do is we're going to draw green arcs linking up all of the green vertices, which we can link up without crossing a loop. And then we do the same also for the orange vertices. Okay, so we draw a bunch of extra arcs that are kind of linking up the half integers, which cannot be disconnected from each other by meandric system loops. Okay, and it's not too hard to check that all of the orange vertices, every orange half integer is going to be separated from every green half integer by a loop. So you can never find an arc joining orange and green which crosses one of the black loops of the meandric system. All right, and this is a consequence of like a parity feature of these perfect matchings of the integers. Okay, so for this reason, we can think of the meandric system as being kind of a percolation model. All right, we can kind of think of these green edges as being the open edges, the orange edges as being the closed edges, and then the loops of the meandric system are like the interfaces between the open and closed clusters. Okay, so it's kind of a similar situation to the loops that you generate from like a percolation or Ising or other type of spin model configuration on a fixed lattice. Okay, and this it's kind of natural to compare this meandric system to the setting of site percolation, say on a fixed lattice, because it's known that for critical site percolation on the triangular lattice, the interfaces between the open and closed clusters are converging to this conformal loop ensemble with parameter kappa equal to 6. And we conjecture that the same is supposed to be true for these meandric system loops. So it's kind of natural to think of them as, yeah.
Can you just say again more slowly how you get these colors? I just somehow
okay, so you look at all of the half integers.
all of the half integers.
So z plus 1/2.
And you just alternate.
And you just alternate the colors. Okay. And then whenever you have two half integers, which can be joined by a path which does not cross any of the meandric system loops, you draw that path. Okay, so
these paths, they will just be, I guess you get the trees.
Yeah.
Loops, I mean, what?
Yeah, so these paths are not necessarily going to form loops. Like you can have like two loops of things which are joined together. Yeah, and you can have like ends that are not linked up to anything. So it's like some collection of loops and trees, I guess.
And then the green paths.
So kind of the orange and green have the same sort of behavior.
So the black is just the interface between these two.
Yeah, that's right.
And do you have in mind a planar map somehow that this lives on?
Well, I mean, you can view you can think of a planar map. You can think of a planar map, which is just the union of the green edges, the orange edges, and the segments of the real line. Or I guess the half segments of the real line joining the half integers. That's a planar map, which is not exactly the dual of the original planar map, but is kind of related to the original planar map in some way.
Large faces, I guess.
No, I don't think it. Or yeah, I guess it can have some large faces. Right. Okay. So there's some kind of planar map, which is the union of the union of segments of the real line and the orange and green clusters. For which we can view the meandric system loops as being like the interfaces separating the clusters. It's then interesting to kind of think about what is the analogy between the results and questions in the theory of meandric systems and the results and questions in the theory of percolation on a fixed lattice. Okay, so the existence of macroscopic loops in the infinite meandric system is kind of analogous to like the existence of macroscopic loops or macroscopic clusters in critical percolation on a fixed graph. Okay, because it's not too hard to see that if there's an infinite meandric system loop, if there's a macroscopic meandric system loop, then it has to be separating like a macroscopic orange and green cluster. In a similar vein, showing that there's no infinite path in the uniform infinite meandric system is kind of analogous to showing that there's no infinite cluster at criticality for a percolation model on a fixed graph. Okay, again, because if you look at the infinite volume version of this, it's not too hard to see that existence of an infinite path is equivalent to existence of infinite green and orange clusters. Okay, and then a result about no infinite path in the half plane version of the meandric system can be thought of as kind of being analogous to to having no percolation at criticality. If you take like a fixed lattice, like a triangular lattice, but then you remove one infinite ray from it. So we show that kind of, once you remove one infinite path in the dual that goes to infinity, then you can't have any infinite clusters. Okay, and there are some analogous results to this that have been proven for various types of lattice percolation models. So let me end the talk there, and then just open up for questions.
Any question?
Yeah. Do your results show that if you look at the loop containing the origins, that it, I'm not sure I know how to formulate that the diameter of it in terms of 1 up to n is little o of n. So the leftmost point visited and the rightmost point visited are little o of n apart.
No.
Tending to 1.
Yes. So we do not show that. And the reason is that proving that is equivalent to proving that there is no infinite path in the infinite meandric system.
So what would be you would conjecture that the difference of leftmost and right points is n to some power?
Yeah, it should be n to some power, and I think it's going to be. I think if I spend a few minutes doing some calculations, I could probably guess what that power is, but I maybe can't do it just off the top of my head.
Does that somehow hint that there is somewhat independence between regions of this object if you look at distances longer?
Yeah, you do have some independence between different regions. In fact, to some extent, you actually have exact independence between different regions
because of random walk.
Yeah, because the whole thing is encoded by a random walk, and so if you have things that you can set things up so they depend locally on the random walk, you can actually get exact independence statements.
But I mean the loops.
Yeah, but there should be some kind of long-range independence statements for the loops as well. But to prove that, one would have to first show that there's no bi-infinite path.
Right.
That we haven't been able to do in the whole plane setting.
So if you go back to the old work of DiFrancesco and so forth, they did this. How did they do this? This was before SLE.
Yes.
And did they? My recollection is they did this with some kind of conformal field theory and random matrix theory combined.
Yeah, that's correct.
So can you say something about that?
Okay, so maybe a very quick summary is that this meander can be viewed as a special case of the O of n times n loop model, or of the fully packed O of n times n loop model.
Yes.
But on a planar map. Okay, and with n equals 0.
Okay, not on
Z2. Not on Z2, but what they were doing is they were looking at this fully packed O of n times n model on Z2, and they had some heuristics that suggest that you should be getting some conformal field theory in the limit for this. And there's also some sort of general heuristics that if you have some lattice model, which is giving you a certain kind of conformal field theory, then if you do the same model, but on a planar map instead of a lattice, then you should be getting. Yeah, it's related to this Nitzik, Polyakov, Zamolodchikov thing. Yeah, so that's kind of the origin of this heuristic.
So they go from the lattice, from the regular lattice to one of these random
yes
lattices, 2-dimensional lattices, right?
Yeah, and this step of,
and then there's a dictionary that takes you back and forth between the two.
So there are some subtlety between the central charge, which is if you on regular lattice, if you're fully packed,
Yeah.
then the central charge is like increased by one because of additional height function.
Mhm.
But for random lattice, you don't have this additional height function.
Yeah.
Central charge is just -2,
Yeah.
which is like so central charge is just -2 plus -2, which is -4, and that's exactly this gamma value.
I see, yeah.
So when you define the meander system, it could be, so you use two independent simple random walks. So that is one way to characterize. But if we now replace the two simple random walks by say two correlated simple random walks, so I guess probably we could also get some scale limit with different kappa.
Yes, that's
But
correct.
the question is the corresponding loop still CLE6 or are there different different kappa?
So that's a good question. I think that the loops should still be CLE6.
Okay.
What you should do is you should have like you'll change the value of gamma and kappa in the way that you would expect based on the correlation of the walks. And then you'll still get a CLE6.
Okay.
And I think a lot of our techniques still work if you have correlated random walks. And so one should be able to prove somewhat similar statements in that case. But we don't have maybe such a nice combinatorial interpretation of the model where you have correlated random walks.
So why do you still conjecture this is still CLE6? What is the
Okay, well, you're going to have by mating of trees, you're going to have SLE kappa with a matched gamma LQG on here, and then you want the central charges of the SLE models on the planar map to add up to the central charge for the LQG.
okay?
And so the central charge for the loop model is going to have to be 0, and that gives you kappa equal to 6. So that's maybe not a completely
This is-
solid heuristic,
Yeah.
but that's at least my guess. So what should be happening? One could confirm this by simulating the correlated model and seeing if the exponents are what they're supposed to be.
So I have another question, which is so here, so given this particular Owen loop on planar map, you have this diameter boundary.
Yeah.
And are there any other like Owen loop type model on planar map? You have these type of boundary diameter.
Well, there's some version of the Ewain loop model on planar maps, which is related to these alpha stable maps as studied by Korean and Legal and
But there they already removed the cycle, the large faces.
right.
But here your bound is for the original.
Yeah, so for that version, I don't think they're able to get diameter bounds for the loops viewed as subsets of the original planar map. So I guess you could just do percolation on a uniform triangulation, and then you can bound the diameters of the loops. But
So you know a lot about statistical mechanics on these random graphs.
Right.
Like,
Actually,
graphs.
not
yeah,
But
much for the
but maybe not so much for the ON. Is that the problem? Or
right. So like the things that
for Ising, I think you can solve like more or less.
for Ising and a planar map, also not so much as known.
Yeah, so here the difficulty is you need to know the diameter for the map. This is not something can be
Yeah, you can compute the partition
yeah,
function.
that's not
all that.
tractable from
That's not enough to.
like CFT calculation, random measure.
Okay.
Those are not.
So there are some specific statistical physics models and specific types of planar maps where we have a fairly good understanding of stuff, but it relies on having some exact combinatorial tools for analyzing it, and this is not available for all
So,
types of
yeah.
models one might want to
So
consider.
for Ising, you can solve, I believe,
Yeah, you can solve anything.
lots of
Correlation
things.
functions.
Percolation and also, right? You can do that on these, because there are just various recursion relations you
Right.
can get and then solve for them. They're not trivial, but you can solve.
Yeah.
So this is different because what? I mean, because you have ON models or
So
or you're after diameter, maybe you're after.
Yeah, so kind of
different geometric questions.
Yeah, so kind of the key tool.
Yeah.
Yeah.
After different coding questions.
Yeah, so the key tool that makes this model tractable is that we have this bijection with the two random walks, and so we can get some independence out of these random walks, and there's also a fairly robust theory developed for proving things about planar maps encoded by pairs of random walks. And so we have also these kind of tools at our disposal.
So
Yeah.
Claire, if you replace the law of the pair of random walks, something that converges to a correlated pair of random walks.
Yeah.
Maybe you were just saying this before, but you still think it's SLE6 no matter.
So I think that you should get like the matched gamma and kappa for the LQG and the Hamiltonian path. And then you should also get a CLE6 for the loops.
Right, so you think it's always a 6,
Yeah.
just because
Center charge is no.
these paths go along and they
Yeah.
bounce off stuff. There's enough local
Yeah.
knocking them around that they don't feel the large.
Yeah. I think that's maybe a reasonable way of thinking about it.
Are there any, and maybe this is too much to hope for, but if you had something like what Shin did, where you have the coupling where you get exactly percolation, or that.
You have a percolation on top of percolation. Yeah.
So you want two percolation or what do you?
I mean, so you can take the correlation to be 1/2, right?
Yeah.
And then you have a side percolation on top of the triangulation.
I
This
see.
is already a percolation.
Okay.
Then you have another one, which is this.
Yeah. Okay. So then you have two things that are supposed to be converging to independent CLE6s.
Yeah, and there might be sort of a bijection from one to the other so that they're actually equivalent, not just equivalent in limit and law.
Right. Well, I mean, if you do the correlation 1/2 one, then you get a CLE6 coming from the like you get like this Hamiltonian path is going to give rise to a CLE6, but you'll get an independent CLE6 from these loops.
Yeah,
You
that's
have a-
right. But then if you swap the two CLs.
Oh, if you swap them, is there?
Is it symmetric under that swap?
Probably not. But you know, maybe there's some miracle that it turns out that it is. You know, it's possible. Yeah, I mean, it's worth maybe thinking about for a little bit. Yeah.
If you take, say, the infinite version, and then you remove the kind of resample the random walk on a larger segment.
Yeah.
So you have these dangling ends coming from outside the segment, and the resample of the random walk in the segment gives you a new matching of these ends. Do you know the law of this matching? Is it uniform if you take a large enough segment or something, or not at all?
I don't know the laws of matching of these ends. I think it's quite complicated.
It's not at all probably uniform somehow, no possibility.
Yeah, probably not. It's I mean, maybe you can conjecture some kind of descriptions of some statistics for this based on formulas for CLE6. But yeah, I don't think we have a exact. I don't think there's any exact description of it at the discrete level.
Okay, so maybe you can save more questions for lunch and the lesson.